I'm Seung-jae Lee at FIU. So in this second part of presentation, I am going to talk about experimental computation simulation of wind damage to facades. So this presentation was made possible in collaboration with many of my colleagues, so listed here. Just so all the credit should go to them. I'm just making the presentation on behalf of the team. All right, so before we start, I just like to briefly mention the wind tunnel experiment option in VUQ. Frank provided a great overview of a VUQ, but I just like to re-emphasize this option, wind tunnel test experiment option, because it enables us to perform it's kind of streamlined wind tunnel test to FE simulation. So to use this option, this info file is needed in JSON format, which has the information of specimen geometry, pressure tab locations, and measured the CP, pressure coefficient values. So FIU Wallowin EF can provide this sort of wind tunnel test data. So users can streamline this experiment to simulation process with uncertainty quantification VUQ using VUQ. So this type of CP time history can be put in the last part of this info file. All right, so this is the menu that I will serve today. So in omakase style. So let me first provide a quick overview of wind damage to building envelopes. And then let me move over to introduce our ongoing research currently conducted at FIU to show you or to demonstrate how we may be of help to your facade research if you work with us in the near future. And then let me wrap up with some brief dessert with some concrete remarks. All right, so many high-rise buildings use cotonneau systems as the main cladding component. So these cladding components remain the most vulnerable part of the buildings under wind loads. So as you can see in these photos, the wind damages are often made to building envelopes in extreme winds, although the buildings, the structure survived. So this type of cladding failure is a leading contributor to astronomical economic losses in wind events, which are often estimated more than $30 billion per year in the United States. So there are several different types of facade damages we can observe during and after extreme wind events. So including like frame deformation, glass cracking, blowout, things like that. Upper part, so for openable window, is connected to the main frame using the metal hardware. So wind-induced vibration may cause this type of disengagement. And also wind-induced vibration can affect the joint quality and then also the amount of water intrusion into the building interior. Okay, so why this study is important? Why do we need to study wind impact to building envelopes? Because it is obviously the most vulnerable components, and wind-induced vibration impacts the water tightness of these building envelopes, so which renders the building unusable with the water intrusion. So damages, it makes damages interiors and also utilities. And also this study may significantly contribute to enhance the performance-based wind engineering framework, because majority of performance-based wind engineering research has focused on the performance of building structure itself. So our tools, including VUQ, has limited its focus to the same scope of the study, so to assess the structural building response. And current building codes centered on equivalent static analysis can be also improved. And furthermore, ASC 7, the current ASC 7 may be misleading because it says structures with natural frequency above 1 Hertz do not need to be analyzed for wind-induced dynamic effects. But it's the 1 Hertz limitation for vibration effects was originally proposed with the typical building size in mind. So this code is focusing on the dynamics and the vibration of the whole building, not the facade system. So this may not be directly applicable to understand the behavior of the facade. So there are many flexible and slender elements in facade systems, such as a fin, shade, and upper window. So significant vibration may occur with natural frequencies as more than 1 Hertz. So indeed, in our the full-scale Wallow wind testing, we have witnessed significant wind-induced resonant vibrations in these cladding systems with a natural frequency as high as 14 Hertz. So So I think this current code can be improved. But understanding the behavior, understanding the performance of the facade system is not really straightforward because this facade system is a complicated the mechanical system. It has many framing elements, many mechanical connections. So there are some variations depending on the company, types, and brand. But I would say most of the facade system has these five components, the parts, and connected through these mechanical connections. So definitely there is a glass in the facade system that is connected to the chassis frame in case there is an operable window. And those are connected through the pocket, the frame pocket, which has a beading, several elements, beading, gasket, structural glazing, and so on. And in case there is an operable part, and then the chassis frame is connected to the window frame, and those are connected to using metal hardware because that needs to be opened. And also window frame is connected to a mullion transom using the mechanical couplers such as thermal brick. So here mullion transom is a vertical and the horizontal member of the main frame. And then this mullion transom is connected to the building structure elements, so such as like a flow, the columns, and these are connected through the metal hardware such as anchor bolts. So the wind load imposed on the glass is transmitted up to the building structure here through a number of the framing elements and number of mechanical connections. So it is not quite straightforward to characterize all the properties and how those are contributing to the performance and the behavior of control system. And also, the performance and behavior of this facade system depends on construction workers, the installation skills and experience. So, meaning there are human factors. So there are inherently high uncertainties in the predictive facade system performance and behavior. So hopefully, in my personal opinion, so there will be needed. So we might need a enhanced tool that can assess those uncertainties in the performance of the facade systems. All right, so at this point, I'd like to introduce two ongoing customer research currently conducted at the FIU Wallow Wind. The first one is funded by NSF IUCRC WIP Center, so Wind Hazard and Infrastructure Performance Center. So for more details, you can go to this website, wipc.org, or you can just directly ask our Dr. Jesus, who is the site director. So this project is focusing on investigating the interrelation between the wind-driven rain and wind-induced vibration effect on the customer systems. And we are working with our industry partner, Dr. Guido Rory at Pumastilis Group. And then second project, the study is focusing on the performance of overall part of the facade system. So those are interrelated projects. We are also working with Pumastilis Group on this project. Okay, so this is a specimen provided by the Pumastilis Group. So this is overall dimension. So 12 feet width, the 6 feet depth, and 10 feet height. So this is a full-scale specimen, and this specimen is two-sided. So front is with actual cardinal panels, where the accelerometers and the strain gauges are installed. And we couldn't put the pressure taps here because the drilling on actual glass is not feasible. So we decided to put it on the other side, on the rear side with the polycarbonate panels, because drilling on the polycarbonate is much easier and also feasible. So these black dots indicate locations of 110 pressure tap locations and on polycarbonate panels. By the way, there are 3 panels here. So mid panel is the main panel, and we have 2 side panels. So to instrument these pressure taps, we drill the hole and instrumented the taps and put the data logger like that. And these dots indicates the location of accelerometers and strain gauges. So we put the 3 accelerometers in the middle panel, and then we put about, I think, 23 strain gauges on both sides of, on both inside and outside of glasses, and also mullion as well. The specimen is located on the Wallow Wind turntable, and we measured pressure coefficient CP and also dynamic responses while we rotate the turntable to see the directional effect of the wind flow. So here, 90 degrees indicate the wind flow that is normal to the glass panel. So CP was measured for the wind speed of the 50 miles per hour of the wind speed. We tested for 60 seconds, and the acceleration and strains were measured up to 90 miles per hour of the wind speed for a longer test duration to see. So we wanted to better observe the dynamic responses of this Coulthard system. All right, so this is a time history pressure distribution we could obtain. So with the CP measured from this test, we could retrieve that the pressure distribution like that. So again, well, this data can be directly used with the SimCenter tool, VUQ. So you can streamline your wind tunnel experiment to FE simulation. So that is a great benefit of doing wind tunnel testing and then using VUQ software developed by SimCenter. All right, so we cross-checked our test result with NIST data. But there is no exact same model available in the NIST database, so we chose the closest one as possible. So here, the height to width ratio is, for example, a little bit different. Roof type is a little bit different. But we wanted to at least qualitatively compare, so to make sure we are doing things right. Right, so this is a CP mean values we could obtain from the mid height of the specimen. So as you can see, so the blue one is a wild test result, and the dotted line is NIST data. So as you can see, overall good comparison shown between these two data. Okay, so I think I'm sure the experiment team did a very good job on that. All right, so this is also we measured the acceleration time history. So this is one of the example measured at the center of the middle panel. So to X, Y, Z directions. And also, this is strain data obtained for this wind speed, and this is one of them. We have a lot of strain data, but just to show you. So this is the strain data that is measuring longitudinal deformation of this vertical mullion. So, so this strain and acceleration time history were used to calibrate the numerical models of the Coulthard system to be discussed in the following slides. Right, so let me talk about the numerical model briefly. So our test specimen has an opera part, meaning it has a chassis frame. In case there is no opera part, there's no chassis frame. But anyway, we have the opera parts. So we have chassis frame as well as a main frame, which is composed of mullion transom, which are the vertical and horizontal members. And this chassis frame for openable window is supposed to be put on this location. All right, so we use the 12-degree freedom 3D beam elements to model this frame elements. And then we realized there are 9 different framing profiles we need to model. So here, these two are the transom profiles, or actually 3. So 5 and 7 are on top of each other. So these are transom profiles, and these are mullion profiles. So vertical members, these are horizontal members. And as you can see, all the members, all the frame members have different profiles, as you can see, except this chassis frame. So we computed all the geometric properties, including area and torsion resistance, area, moment of inertia, and things like that, based on the CAD drawing. And then computed this one and reflected these properties in the beam elements when we developed the numerical model. So this is, for example, profile number 2. So this is mullion here and here. And then, so this one is for profile number 6. That is the top transom, like that. And so we also need to consider the interaction between the frames. So for example, here, number 2, number 1 are interacting, 5, 7 interacting, and so on. In the frame number 3 is also composed of 2 parts. So it looks like this is continuous, but it's not the case. So also the interaction need to be considered, and so on. And chassis frame also need to be put on top of this main frame. Also, the interaction need to be considered. So, for example, so here, this is to model the interaction between the mullions between these panels. So we have 3 panels here. So we just adopted translation and rotational springs for all directions. So in that way, we could model the interaction of the mullions between the panels. And this is we use the same strategy to model the interaction between the mainframe and chassis frame. So here we did the same thing, pretty much. But we didn't, in this particular case, we didn't model the rotational spring because we couldn't anticipate rotation resistance and between these two interactions. But anyway, so we basically use the same approach. And in the end, we could assemble this chassis frame to the mainframe. So this is everything so far. So configuration, and then the interaction, the springs modeled to model the interaction. So next is how can you model the class properties, and then how we can assemble those. So class modeling is important because it covers, class covers most part of the facade. So it significantly affects the dynamic behavior of the facade system. And so it is a great importance to accurately model those properties, including mass, stiffness, and so on. But the modeling class is not really quite straightforward in case there are multiple layers with the insulated laminate glass, which is actually our case. So here, the glass used in our test specimen was a DGU, double glazing unit, meaning it has inner glass layer and outer glass layer that is separated by thermal spacer. So that there is a gap between these two. And also inner glass layer is laminate glass, which has a PBB interlayer, which is sandwiched by two layers of glasses. So we wanted to compute the equivalent glass thickness of this DGU glass, because that makes simplifies the modeling a little bit more simplified rather than just modeling the whole thing. So we adopted Galuppi's formula in 2012. So she developed a nice formula such that we can estimate the effective thickness of the laminate glass, and with this we could compute the effective thickness of the inner layer. And then with that, we could use the Eurocode to estimate the effective thickness of the DGU unit. So we used the finite element software to back calculate the overall effective stiffness, and then that information used to compute the the equivalent thickness of the DGU, right? Okay, and then these are some numbers all the numbers we considered in estimating DGU thickness. So this is the final numbers we adopted for modeling the glass thickness. But the thing is, the thickness is thinner than some of these two. So some of outer layer, inner layer is thicker than the DGU thickness we adopted. So I just summarized here as using thickness ratio R. So if that is less than 1, that means the equivalent DGU thickness is thinner. So we deliberately increased the unit weight to make the mass the same with the original DGU, and to make the same dynamic property compared to the actual the specimen. So we scaled the mass, and then unit weight to make the same mass, and then those are the values we adopted to make the dynamic behavior comparable to actual one. And the silicon joints are joining these frames and the glass. So those are located between the main frame and glass and the chassis frame and glass. Likewise, this is elevation view. So the main frame, so transom is a horizontal member of the main frame, and the glass, so and then like that. So we also model this silicon joint using the same strategy. And then finally, we could model this frame and silicon, and then we could assemble with the glass. And then finally, this is the modeled Computational system we developed in the numerical model. And boundary condition was modeled as considered in the actual test specimen. So we really considered how that was attached to the metal structure used in wallowing testing. So we put a simple support like that. And then we didn't consider any vertical deflex at the bottom of the transom to mimic the actual condition in the testing. This is again analysis result. So first and second mode could be observed at near 5 and then 18 hertz. And the rest modes, the higher modes, third and fourth and fifth mode, are near at 24 hertz. So these values are overall comparable to the power spectral density spikes observed from wall of wind testing. So as you can see here, the first, second, and third spikes are near at 4, 18, and 24 hertz. And this is the eigenmodes. So, and the middle panel are excitated in the first and second mode, and then the side panels are excited in the higher modes like that. Okay. And we also perform time history analysis. So we use the pressure time history data to apply the time history nodal loads. And then this is the simulated the behavior of the control system for 50 miles per hour wind speed at 90 degrees of the wind direction. And then we compare the acceleration at the center of the middle panel. And then this is just to compare the, well, we have other data as well, but this just for example. And then we could see overall good comparison shown between the FEM data and wall of wind. So FEM is lighter green and wall of wind test data is darker green. And then the displacement is shown like that. So maximum displacement was like 0.25. And then we wanted to see, well, 50 miles per hour is not much compared to Hurricane Cat 5 pressure, but Cat 5 wind speed, but we just wanted to see how much dynamic amplification is shown. So we could say, we could get the mean pressure time history from the pressure tab data. And then, well, we could get like estimate the mean max of this mean pressure is 0.035 psi, and apply this one as a quasi-static pressure. And then we obtain the displacement at this point at the 0.219. And then dynamic amplification was about 15%. That is pretty much comparable to what we directly obtained from wall of wind testing. Right. So, well, this is ongoing research, and then I believe there is much more to come regarding the experiment and simulation. This is just to show you, and also hopefully there's another chance we can talk about this one in more detail about the behavior and how the testing was done and how we could analyze. But the take-home message in this presentation is we can help if you like to perform the facade research with us. So that is the key message. So just to conclude, building envelope is the most vulnerable part of the wind loads again. And there are high the complexity and uncertainties in the response of facade system because of many reasons that I described in the previous slide. And I just like to emphasize the third point. So this is relatively unexplored area, relatively, I say, in spite of its importance. So NSF ECI clearly indicated building envelopes as one of 4 research focuses. So this slide came from NSF ECI webinar exactly 3 months ago. So the program directors actually put this building envelopes as explicitly put this one as one of the program's research focus area. So I think this is a great research topic for your next proposal. So when you write the next proposal, please think about, yeah, I hope you can consider to work with us on the experiment portion and also numerical portion, numerical analysis as well. So, okay, so we have a capability and experience. So please work with us, and then thank you. And with that, let me conclude my presentation. Thanks.